Let's try another example here, guys, that relates to the acceleration that we've been talking about over the last few days here. Example 1.15 on page 51, it says a speedboat slows down at a rate of 5 meters per second squared and comes to a stop. If the process took 15 seconds, find the displacement of the boat. How far did the boat travel during that time that it was slowing down? Now, maybe it traveled 100 miles before that. That's not the question. The question is, how far did it travel during the time that it was slowing down, during that 15 seconds? All right. So is this a group A or a group B problem? Remember, group A, V equals delta D over delta T. Group B, all of those acceleration equations. There's 5 of them, and they're on our data sheet. We don't need to memorize them. We can try whichever one we want if it's a group B problem. So what is it? Group A or group B? It's group B, right? It's an acceleration problem. Now, it's slowing down, not speeding up, but that's okay, because acceleration is slowing down or speeding up. Is there anything in here that you think you might like to use a red pen for, to circle, to underline, to highlight, to draw attention to, that we might make a silly mistake somewhere? Yeah? Okay, it comes to a stop. Okay, that's kind of a given, right? Like kind of one of those things that we write down as givens, but it's a read between the line given, right? We're not told that VF is equal to 0, which is really what that means, right? We're told that it comes to a stop. So yeah, we should draw attention to that somehow, whether it's with our red pen or somehow we should draw attention to the fact that it comes to a stop. It slows down. So what's important about that? It's slowing down. Good. So this tells us that VF is 0. This one tells us that this is a negative acceleration, right? We want to notice those things. We want to notice those things before we actually go to solve the problem. Now, if we don't, we may be fine. We may write down the equation. We may plug the numbers into the equation correctly and not forget that 5 should be a negative value and not forget that VF is equal to 0. We may catch all that. But we're less likely to than if we identify it and draw attention to it now. So if we see it now, let's draw attention to it now so that we don't forget later on. All right. Let's write down those givens here. We know that A is negative 5.0 meters per second. We know that it comes to a stop. These are the two things that you guys just noticed for me. The F is 0 meters per second. We got a time here of 15 seconds. I think that's it, isn't it? What are we looking for here? The displacement. All right. So we're looking for delta D. We established that it's a group B problem. We know it's one of those 5 equations. Take out your data sheet and have a look at it. Which one of those group B equations do you want to try? Anybody? V equals D over T. No, it can't use V equals D over T because that's a group A problem, right? Which one do you want to try? The last one? D is equal to VFT minus 1/2 AT squared? Sure, let's give that a try. Now, Ethan, just because you said that one and just because I said, yeah, sure, let's give that a try, doesn't mean it's the best one necessarily, because if you pick a group B equation, when I ask you which is the one you want to try, then I'll take it. I'll write it on the board because they're all valid. This is no more valid than any of the other ones. Okay, this is one you suggest. Let's try it and see what happens. VF is 0, T is 15. Hey, do you know what? I can cross that off. 0 times 15 is 0. I can just save myself the bother of writing down those numbers because the product of those has got to be 0. So it becomes 0 minus 1/2 AT squared, or 0 minus negative 5.0 times 15 squared. Hey, this looks like it's going to work, right? Looks like you did pick the best one or the easiest one to use here. 15 squared is 225. 225 times 5 is 1125 times a half is 662 and a half. Is that right? 662.5 meters. 562? Yeah, you're right, I think. Yeah, I think that's right. 562 62.5 meters. Oh, good question. Good question. Is that negative or positive? Yeah, it's positive. And why is it positive? Mathematically. Forget about physics-wise here right now. Mathematically. Okay. Mathematically, it's positive because negative times a negative is a positive. But physically, okay, let's just take a step back from it for a second and think, why should it be positive? Independent of the math. Why should it have come out to be positive? And it did, but why should it have come out to be positive? Distance is a scalar, although we've solved for displacement there, right? Okay, technically all we needed, no, it actually asked me for displacement, so I did need the direction there. Direction north, south, east, west, not sure about that, but we know it's the positive direction, right? Yeah, he didn't go backwards, right? He's going forward. Now he's slowing down as he's going forward, but even as he slows down, he continues to move forward. So if he's moving forward, his displacement has to be forward, even if he is slowing down with a negative acceleration, right? 562.5 meters. Hey, we haven't looked at significant figures yet. How many of you guys have done significant figures? Not very many. Interesting. Okay, we'll leave it then for today. We won't worry about it today. We'll spend some time on it when we have a little bit more time than we have on a Friday. All right, 562.5, 563, round it wherever you want there for now, and we'll deal with sig figs later on. All right, let's see what we can do then with those two questions. Let's have a look up here, everyone. We're going to go over question number one. Number one involves exactly what we did in the last question, right? Writing down our givens, identifying group A, group B, and so on and so on. You know, red circle if it's appropriate to circle anything in red. But this one also involves a little bit of algebra, a little bit of rearranging. And traditionally, people have a little bit of trouble with that. You guys have been doing a much better job than most classes that I've had in the past at rearranging. But that doesn't mean you're perfect at it. Okay? Just because you guys are better than other classes have been doesn't mean you're perfect. So let's spend a little bit of time going over question number one here. It says, if the arresting device on an aircraft carrier stops a plane at 150 meters with an acceleration of negative 15 meters per second squared, find the time that it takes the plane to stop. Do you guys know what that means, the arresting device on an aircraft carrier? No? Sometimes we read a question and we're able to solve the question even if we don't really know what the words mean. But then sometimes the words make us stumble. We can't solve a question simply because we don't know what a word means. The arresting device on an aircraft carrier is actually a hook that sticks down off of the bottom of the plane, the belly of the airplane. And that hook grabs a cable that's strung across the aircraft carrier. So if this is the aircraft carrier, there's a cable that's strung across it. And then when the airplane is landing, there's a little hook like this that dangles from the airplane. And the whole point of that is as this airplane comes down, the hook grabs the cable and it stops the airplane. Why do they have to have that? Well, because as the airplane is landing, as it's approaching the ship here, it doesn't have a lot of distance to land, right? Okay. As the airplane approaches the ship, it doesn't slow down. You know, when you're landing in a regular airplane on a regular runway, okay, you can feel the reverse thrusters, right? You can feel, okay, you're slowing down dramatically, quickly by the jet engines firing the other way, right? When a plane is landing on an aircraft carrier, it doesn't do that. It doesn't fire the reverse thrusters. It doesn't try to stop with its engines. In fact, it does the exact opposite. When you're coming down on this airplane and you're approaching this ship, what does the pilot do? She guns it. Why? Why? It's such a short runway on these aircraft carriers. If you miss and you land too far up on the ship, what happens? You crash into the ocean, right? It's such a short runway. So what they do is as they're coming down, they actually give it thrust as if they're taking off. And that way, if they miss, they can just keep going, right? But if they're thrusting, if they're giving it a lot of thrust and going really, really fast, they got to have some other way to stop. So how do they stop? They got this hook dangling out the back. Basically, if they miss the hook, then they just keep going. If they catch the hook on this cable, then that stops them, right? And then that's, of course, when they're going to fire their reverse thrusters as well, once they know they're safely on this ship. So the arresting device on this aircraft carrier is this hook that grabs this cable to keep the airplane from crashing into the ocean, going off the end of the aircraft carrier. All right, is this a Group A problem or a Group B problem? It's B, right? Pretty much everything we're doing here is a Group B problem. Okay, but I always want you to think of it, because you never know when you might be surprised by a Group A problem. Okay? It is definitely Group B, though, because it's accelerating. It's slowing down. What do we have given to us here? There's no funny units, right? So I don't think there's anything to circle other than maybe that negative, although it is written down as a negative, so you may or may not circle that in red. What do we got given to us here? We have something is 150 meters. What is that? The 150 meters. Yeah, it's displacement. Okay? The airplane moves 150 meters in the positive direction, whether that's north, south, east, west, the positive direction. We have an acceleration of negative 15 meters per second squared, and we're looking for the time, right? Maybe there was something that we should have circled in red here. Maybe there was something that we should have drawn attention to here. Yeah. Yeah. Takes it to stop. So what does that mean? It's kind of a given, right? But it's a read between the lines kind of given. Good. All right. Let's try the same equation that we used for the example. D is equal to VFT minus 1/2 AT squared. Now, this is where it starts looking a little bit ugly. Okay, the only unknown that we have in that equation is T. That's good. One equation, one unknown. The only problem is it appears in two places. I'll tell you what. If you're solving this equation and VF is not 0, then you don't know how to solve this. Okay, you need to use what's called the quadratic equation, and some of you may have learned that in math class already. Most of you probably haven't. Who knows what the quadratic equation is? Nobody? All right. This is therefore impossible for you to solve for T if VF is not 0. Right? Imagine, how would you get T by itself when it appears in two places there and one of them is squared? It's impossible without the quadratic equation. The good news is VF is 0. If VF is 0, 0 times T is 0. So that entire term disappears. So now T only appears in one place. Now I wouldn't say it's easy to solve for by any means, but it's easier at least. This is what my equation looks like now. D is equal to negative 1/2 of AT squared. Solving for T. My general rules of rearranging equations, solving for variables, we get rid of what's not attached first. So if anything's added or subtracted, get rid of that. And then we get rid of what is attached. Well, there's nothing that's not attached here. Right? A is attached to the T. 1/2 is attached to the T. The negative is attached to the T. So we can't get rid of what's not attached. Let's get rid of what is attached. Negative 1/2 A is multiplied by T squared. How do I get rid of it? Nope. Divide. Right? If it's we want to get rid of something that's multiplied, then we divide it. So let's take the whole thing, negative 1/2 A over the other side by dividing. D over negative 1/2 A equals T squared. Then what do we do to get the T by itself? Square root it. So the equation becomes this. It looks a little bit ugly, but it's still valid. D, square root of D over negative 1/2 A. Is that okay? Does the rearranging of that equation make sense to you? Bless you. Let's finish it off here. D is 150. Oh, wait a second. I got a negative underneath there. I can't take the square root of a negative number, can I? No, I can't. So what do I do here? Have I made a mistake? I haven't, no. How do I resolve this if I have a negative on the bottom? Okay. Good. Yeah, it's negative 1/2 times negative 15, right? Square root. So negative times a negative becomes a positive. You can have a negative underneath the square root sign. You just can't have a negative number. 1/2 times 15 is 7.5. 150 divided by 7.5 would be 20. So the square root of 20. And the square root of 20, I assume, is 4.5 there. There we go. I want to take a look at number 2 here. A couple of challenging questions here today, hey? A couple of real challenging questions. Number 2 says, the 1968 Corvette took 6.2 seconds to accelerate to 160 kilometers per hour, or 100 miles per hour. If it traveled 220 meters, what's its acceleration? All right, group A or group B? Definitely group B. Yeah, definitely group B. Anything red pen here? I don't think so. I don't think so. Let's. Oh, yes, there is actually. What's the thing that I'm looking at here? It should be circled with the red pen here. Yeah. We don't want to be in kilometers per hour, right? We want to be in meters per second. Always now. Always. When we're doing acceleration stuff, group B stuff, always want to be in meters per second. All right, we got a time here of 6.2 seconds. We got a velocity of 160 kilometers per hour, which we're going to want to convert in a minute. What is that, though? Is that VI or is that VF? VI, VF. It accelerates to 160 kilometers per hour. It's VF, yeah, definitely VF. The displacement is 220 meters. And the directions of both of them are north, so we might as well just leave north as positive. We want to find the acceleration. The equation that you're going to use, I think, is this one. D is equal to VFT minus 1/2 AT squared. Although, you can try any of them. Any of them are valid. You just might not have success with another one, that's all, because you just might not have the right variables in it, that's all. All right, solving for A here. Solving for A, that's a tricky question. Some of you guys like to rearrange equations after you plug numbers in. That's fine. I like to rearrange equations before I plug numbers in. That's fine. Doesn't matter. Okay? I'm going to do it before I plug the numbers in here. I want to get A. Remember what we said for the last question? Get rid of what's not attached first. Tell me, please, what is not attached to the A? What variable is not attached? What variable is not variable or variables are not touching the A? Yeah, notice? Okay, distance is already on the other side, so we're not going to worry about that one. Final velocity and that time is not attached. So these things aren't attached. The 1/2 and the T are attached. So what I'm going to circle in green here is not attached. What I'm going to circle in red is what is attached. The -1/2 and the T squared are attached, right? Because they're multiplied by A. That make sense? If it's added or subtracted, it's not attached. If it's multiplied or divided, it is attached. Get rid of what's not attached first. Get rid of what's in green first. How do we take over something that is added to the 1/2 AT squared? Some of you might look at this and say, no, wait, it's subtracted. No, it's not subtracted. It's added. -1/2 AT squared is subtracted. Right? This is added. So how do we take something that's added over to the other side? We do the opposite to it, right? What's the opposite of add? Subtract. So let's take it over. Let's take the VFT over by subtracting. D minus VFT. We can take the whole term over there at once. That's fine. You good? And that equals negative 1/2 AT squared. That's what I've got left. Now, on the right-hand side, besides A, which is the one I'm looking for, the only thing I have left are things that are attached. The negative 1/2 and the t squared. How are they attached? How are they attached to the A? They're multiplied. Both of them are multiplied, right? How do I get rid of them? The opposite, divide. So let's take negative 1/2 and the t squared over at the same time by dividing. It becomes d minus VFT, because that's what I already got on the left side. Everything on the left side now divided by negative 1/2 t squared equals A. See what I've done there? I've got rid of what's not attached, and that's always going to happen by adding or subtracting. Then I get rid of what is attached, and that's always going to happen by multiplication or division. Since I added VFT here on the right side, I take it to the other side by subtracting. Since I multiplied negative 1/2 and t squared on the right side, I take it to the other side by dividing. So that's kind of an ugly looking equation now, but it's a perfectly valid equation. Doesn't matter what it looks like. Let's say now A is equal to D, which is 220, minus, we got to convert that to meters per second. Anybody have that? 54 point. And you got that by multiplying by 1,000, dividing by 44, multiplying by 1,000, dividing by 3,600. Let's multiply that by the time. What was the time? 6.2. And we divide that by negative 1/2 of 6.2.
Good afternoon,
squared.
Students.